So in this section, we're going to look at polynomial functions, and we're mostly just going to look at the graphs of them, how to figure out certain behavior of each polynomial. In your homework, you'll see some applications of it, so you'll be able to see how we can utilize them in the real world. So the first thing we're going to go through is a power function, because this is going to help us a lot when we start applying those transformations we learned from the first unit. So a power function of degree n is just a very specific polynomial of the form ax to the n. N is going to be a positive integer, and a is not a non-zero real number. Could be positive, could be negative. Now what we're going to look at is specific power functions. So we're going to start by looking at ones that have even degree. So we're used to the x squared graph. That's just our basic parabola. So it's got a shape that goes upward. If you try plotting y equals x to the fourth, same thing. If you plug in -1 or 1 in both of these, the output will be +1. If you plug in x equals 0, it goes through the origin. But what happens is it's a little bit flatter inside, and then it grows much, much quicker, okay? If we bump it up and look at y equals x to the 6, if you plug in 0, still goes through the origin. Plug in 1 and -1, still goes through the point +1. So this should be a +1 here, and that should be a -1 down here. And then if you go to take this graph, it's going to be even flatter between -1 and 1, and then it's going to shoot up quickly. And same thing on this side. So if you were to do x to the 8th, gonna still have a similar look to the graph, and it'll keep going on. So if you have a power function and the power is going to be even, your domain is going to be all real numbers. Makes no difference. You can still take anything, raise it to the nth power. The range, though, will only be from 0 to infinity. So because it's an even integer, you're not going to get negative values. It's going to decrease for half of the time. So on the left half of each of these graphs, it's decreasing. So it's decreasing from -infinity to 0. And then on the right half of the graph is where it's going to be increasing. So that's from 0 to infinity. And so because of the shape of all of these, and if you go through going through even and odd functions, this is symmetric with respect to the y-axis. So now if we go through and look at what happens when the power is odd. So in all of these instances, you're going to go through the origin. In every case, if you plug in x equals 1, the output will be +1. And then because it's an odd power, when you plug in -1, you'll get -1 as well. So in the case y equals x, that's x to the first power, so it's got an odd degree. That's just our standard line. You plug in y equals x cubed. We've seen the graph of this before. It's kind of like an S. And then if you look at the graph of y equals x to the 5th, it's similar, but again, it's going to be flatter in between -1 and 1. So the graph would be similar, but just kind of pushed together a little bit more. So when n is odd, your domain is still going to be all real numbers. In this case, you do get negative values, so your range is from -infinity to infinity. When you just have a 1 out front, function's not going to be decreasing. It's always going to be climbing up in all of these instances. So it's actually increasing from -infinity to infinity. And because it is an odd function, it is going to be symmetric with respect to the origin. So this is going to be useful for us because even if I apply transformations and I do reflections, the end behavior is still going to be similar for even polynomials versus odd degree polynomials. Another useful thing that we're going to need is how to find real zeros of polynomials. So we've dealt with this a bit before, but based on those zeros and based on that multiplicity, we're going to be able to know a lot more information about the graph. So first and foremost, we know if x equals a is a 0 of a specific polynomial, then really you get a few pieces of information. The first one because it's a 0, that means when you plug in that value of a, the output is 0. So these correspond to the x-intercepts of the graph. And also it tells you what the factors of that function are going to be. So you get all that information just by knowing that something is a 0. The multiplicity is going to tell us what the behavior of the graph is at that specific intercept. So in the case that x equals a is a 0 of odd multiplicity, your graph is going to cross through the x-axis. If it's even multiplicity, it's just going to touch the axis, but it's going to come right back around. So what that means is if we look at two cases, I've got a on the left, a on the right as well. When you have an odd degree and you have a 0, you're going to go ahead and you're going to cross through the x-axis. But in the case that a is a 0 of the function and it's even, you're going to come up to that point and then you're going to go right back down. So you're just going to touch the axis, but you won't cross through it. So this is really useful for that behavior of the graph. And if you kind of notice in each of these cases, let's even make this one a little bit more smooth, kind of like a parabola. You can see it kind of turns. And we can even make this more complicated. Maybe this is a 0, but maybe I have another one that continues on later. So in between the zeros, my graph is going to have to turn around to be able to come back to the x-axis. Even if you have an odd one and it crosses through here, maybe you've got another 0 and another 0 over here. A few different times the graph has to turn around to be able to come back to the axis. So where that function changes from increasing to decreasing or the opposite way, those are called turning points. And for polynomials, we know exactly how many turning points there can be at most. So a polynomial of degree n can have at most n minus 1 turning points. So if you think of a third degree polynomial, you know there's at most 3 zeros. There's exactly 3, but they could be repeated. There's going to be at most 2 turning points. So kind of like there's going to be 2 humps to the graph. So there can be at most n minus 1 turning points for an n degree polynomial. But if you do have 2 consecutive zeros, there has to be at least 1 turning point in between those two. So it's got to start at that axis and then it's going to have to come right back around. So you're guaranteed a turning point somewhere in between 2 zeros. There might be more, but there's going to be at least 1. So now that that helps us a bit with the graph, we want to think about the end behavior for any arbitrary polynomial. So if you have an nth degree, you're going to have this dominating term, which is ax to the n. So it's basically that leading coefficient and the degree of the polynomial. Based on the value of a and based on whether n is even or odd, will tell you what the end behavior is going to be. So in the case the coefficient out front is positive and the value of n is even, you can think of like 2x squared, 3x to the 4th, 9x to the 10th power. Those are those dominating terms potentially of a polynomial. The end behavior is going to be just like that of a parabola. It's going to be up, up. What happens in between we don't know. Could kind of have a shape like this, but we're going to put dots just because we don't know what the zeros are. We don't know if there's turning points, what happens. In the case that a is negative, kind of like negative x squared, the end behavior is going to be down, down, because that negative coefficient out front is going to tell you to reflect over the x-axis. And again, don't know what happens in between. We just know about the end behavior based on the value of a and n. Now, when you have an odd power, an odd degree polynomial, it's going to be just like the function y equals x cubed. So if the coefficient out front is positive, you're going to have that behavior where it's down left, up right. What happens in between, we don't know, but you can think of like y equals x cubed. In the case that it's negative, everything gets reflected. So now it's going to be up to the left, down to the right, and stuff happens in between. So let's go ahead and take a look at an example. Let's consider a specific function. We'll try to get a lot of different properties about it, and then we'll go ahead and ultimately graph it. So we've got the function negative x cubed plus 4x squared. We want to list each zero and its multiplicity. So we've got our function. Both of them have an x squared, so we can go ahead and factor that out. And to find the zeros, we want to set this equal to 0. So we set each. This is x squared equals 0, x minus 4 equals 0. That really tells us x equals 0 or x equals 4. X equals 4, that factor only happens once, so it's multiplicity 1. But for the x squared term, that's technically a multiplicity 2 because it's x times x. That 0 happens twice. So now that we have the zeros, let's determine whether the graph touches or crosses at each of those intercepts. For x equals 0, it's an even multiplicity, so it's just going to touch the graph there. X equals 4, it has odd multiplicity, so it's going to cross through at x equals 4. Okay. So now that we know that, let's go ahead and find the y-intercept and find a few other points in the graph. So the y-intercept, we just go ahead and plug in 0, but in this case it would be negative 0 cubed plus 4 times 0 squared. So your y-intercept is really just 0, 0. So if we find a few more points, if you go ahead and plug in 1, you'll get 3. Plug in negative 1, you'll get 5. And if you plug in 2, you'll get 8. So you've got the point 1, 3. You've got the point negative 1, 5, 2, 8, and then our y-intercept is at 0, 0. So now let's go ahead and let's determine the end behavior of this function. We've got our x-axis. We know 0 is important and 4 is important. At 0, we're just going to touch, and at 4, we're going to cross. But if we look back to our original function, it's odd degree, and this is less than 0. So because of that, a is negative 1, which is less than 0. It's the opposite of y equals x cubed. So it's going to be up to the left, down to the right. And then we know at 0, it's just going to touch. So the graph's going to have this shape. And then it's going to cross through at 4. So it kind of gives me a good idea of what our polynomial is going to look like. So now we can go ahead and sketch everything. You plug in 0, we know we get 0. You plug in 4, we get 0 as well. If we go back to our other points, if you plug in 1, you get 3. 2 gives you 8, which is all the way up here. Negative 1 gives you positive 5. So we know we're going to have to come down. We touch the graph at 0, come back up, and then I've got to go ahead and turn around and cross through the x-axis at 4. So this is a decent drawing of our graph of the function. Okay. So now let's try another example. Let's find a polynomial function of least degree that has to have the graph shown below. So if we kind of take a look at each of these points, it only touches here. So this tells you it has even multiplicity because it just touches. Same thing at x equals 3, it touches, so it must have even multiplicity. If it crossed, it would have to be odd. So x equals 3 is a 0 with even multiplicity, and the same thing with negative 3. So I want the smallest degree possible in terms of this ultimate polynomial. So I'm going to pick the smallest even number as the multiplicity. So we'll say this x equals negative 3 is a 0 of multiplicity 2. And the same thing here, x equals 3 is a 0 of multiplicity 2. So both of the zeros will have even multiplicity. If it was odd, you would just say it occurs once. You don't need to do the third. You don't need to say it has multiplicity 5. Those work, but you want the smallest one. Same thing here. I could say x equals -3 is a 0 with multiplicity 4, because that would mean it would just touch the graph there. But I want the smallest degree. So with that, the end behavior of our function also gives us some information. We see it's going up, up, so it's an even polynomial. And that also tells us that the value of a is going to be positive. So we can kind of set up what our graph is going to look like. We have some constant a that we need to figure out. X minus 3 is a 0 with multiplicity 2. So that means x minus -3, or x plus 3, squared are factors of our polynomial. And then likewise, x minus 3 squared has to be a factor of our polynomial. Now the only thing left to do, I have this point here, 0.81, that I can use to find our value of a. So we'll use the point 0.81 to find a. So if you plug in 0, you get a times 3 squared times -3 squared. Well, it's a times 9 times 9. So this is just 81a. This better equal 81, so it tells us that a is going to exactly equal 1. So the polynomial's smallest degree with the graph that was shown is going to be x plus 3 squared times x minus 3 squared. So make sure every time you do problems like this, you put that arbitrary a out front. If you don't put that, you might end up getting the problem wrong because you're given another piece of information that you have to use. Okay. So the last thing we're going to go through is what's known as the boundedness theorem. We're concerned with finding zeros. We know there's a lot of ways to do that. We've got the rational zeros theorem to help us out when you have a high degree polynomial. We've got Descartes' rule of signs to help us narrow down possibilities. Now this boundedness theorem is going to help us kind of figure out, are there zeros bigger than a number? Are there zeros less than a number? So we can narrow our choices down even further. So what this states is we have a polynomial. We're going to let f of x be a polynomial function of degree n with real coefficients and a positive leading coefficient. And this degree you want to be greater than or equal to 1 because otherwise it's going to be boring. It's just a line, or it's just a straight line potentially. So now let's suppose f of x is divided synthetically by x minus c. Two things happen. The first, if this value of c is positive, so say you divide by x minus 3, so that would mean 3 is a 0 potentially. If that value of c is positive and all the numbers in the bottom row synthetic division are non-negative, then your function cannot have a 0 greater than c. Okay? So if you were dividing by x minus 3 and you found out that in the end every single piece is positive in the bottom row, then 3 would be your potential biggest 0. Now the other thing it states is if you divide by x plus something, so like x plus 2, the value of c would be negative. And if those numbers in the bottom row alternate signs, if you have a 0, you get to kind of fit it into the pattern. It can be considered positive or negative. Then you know there's no zeros less than c. So it kind of gives you a way to trap all of your zeros. So the best thing we can do is really kind of put this into practice. Let's show that no real 0 of this particular polynomial is greater than 3. So my coefficient out front is positive. I'm good to go. I can apply this boundedness theorem. So I want to divide synthetically by x minus 3. So we're going to put our 3 out here, and then I'm going to put all of the coefficients of this polynomial, including those zeros. So I've got 2x to the 4th minus 5x cubed. I have no x squareds, 3 x's, and 1 is my constant term. So we bring the 2 down, multiply 2 by 3, add together, multiply by 3, add together, multiply by 3, add together, multiply by 3, and then we go ahead and add together. So if you look at this bottom row and this value of c, c is greater than 0, and this bottom row is non-negative. So what that tells us is there is no real 0 of this function that is greater than 3. So you've got all those options for your rational zeros. You can have irrational ones as well, but you know none of them are going to occur bigger than 3. 4 is not a possibility. 5, 5.222, not a possibility. So it gives us a little bit of narrowing down again. Okay, so let's try one more. Let's show that there are no zeros for this function less than -1. So in this case, we're going to divide synthetically by x plus 1. So all the coefficients stay the same. We just have a -1 up here. So we've got 2, we've got -5, 0, 3, and 1. Bring the 2 down, multiply by -1, add together, multiply by -1, add together, -1, add together, -1, add together. So now if you look, it goes positive, negative, positive, negative, positive. And the sign here is negative. So what this tells us is the value of c is less than 0 and the numbers are alternating in sign in that bottom row. So f of x has no real 0 less than -1. So I don't need to test anything outside the interval -1 to 3. All my zeros are going to be stuck in between these two. So again, this just gives us an option and gives us a way to narrow down our possibilities. But anything that we have that can help us out, we do like, so it is a useful theorem.